All right, this is section 5.3, properties of rational functions. Let's start off with talking about, well, what is a rational function? Because a lot of times students hear the word rational and they're like, I don't know what that even is. The word rational basically means fractional. It stands for the word like ratio, like a fraction, a comparison between two numbers. So whenever you can't figure out what rational means, just think of the word fractional. We're going to be covering the objectives of how to find the domain of a rational function. We're going to find the vertical asymptote of a rational function, or vertical asymptotes. And we're also going to learn how to find a horizontal or oblique asymptote of a rational function. And oblique, another word for oblique, could also be called a slant asymptote. All right, definition of a rational function. A rational function is a function of the form r of x is equal to p of x divided by q of x. Notice how it's written in the form of a fraction, right? So anything that can be written in the form of a fraction is a rational function, where p and q are polynomial functions, and q is not the zero polynomial, because otherwise it would be undefined, and the domain of r is the set of all real numbers except those for which the denominator q is 0, because then that would be undefined. So here p of x and q of x are each going to represent polynomial functions, right? Our domain. Before we get started with number 1, where it's asking us to find the domain, let's review what are the 3 things that we can't let happen when we're talking about our domain, right? We can't divide by 0. Hopefully you guys all remember this, right? And we just mentioned it right now. Dividing by 0 is undefined, so we can't let that happen. Number 2, we can't take an even root of a negative number. So whenever we're asked to find domain, that's one of the other things we need to watch out for. We need to make sure that we don't accidentally end up with any negative numbers inside of even roots. And number 3, you can't take the logarithm of 0 or a negative number. And I know I've mentioned these 3 things to my classes. I just want to make sure, everyone's well aware of them. And, I feel like I just can't mention them enough. Yes, we're still not working with logarithms in this section, but I just figure it's never too early to start planting that seed so you can remember it when we get to logarithms. All right, let's go to our number 1 problem here. Find the domain of the rational function f of x is equal to x divided by x to the 4th minus 1. The only one of these 3 things we have to worry about is number 1, where it says you can't divide by 0. So we need to find out what would be our restrictions on our domain. What numbers, if we were to plug them in for x, would give us a 0 in the denominator of this rational function? I'm not going to worry about the numerator. A lot of times people say, what about the numerator? We don't worry about that when we're finding domain. All we care about is the denominator. So all I'm going to do is set the denominator equal to 0, and whatever I get there, that's what's going to be restricted from my domain. So here I'm going to end up with, I've got x to the 4th is equal to 1. And if I take the 4th root of both sides, I'm going to have to remember to put a plus or minus in front of the 4th root of 1. And this is going to give me x is equal to plus or minus 1. Remember, you always put a plus or minus whenever you take an even root of both sides of an equation. So that's why we put the plus or minus there. So this is basically saying that positive 1 and negative 1 are my restricted values. I'm going to draw a number line for my visual learners, because I know this helps my visual learners understand what our domain is going to be. So it's basically all the numbers that I'm highlighting in green. Those are going to be the numbers that are in my domain. So when I write this out, it's sometimes helpful to write a number line if you're going to be using, especially if you're going to be using that interval notation to write the domain with. So my domain is going to be the open interval from -infinity to -1, union, open interval from -1 to 1, union, open interval from 1 to infinity. Or we could also write this in set builder notation, the set of all x such that x is not equal to -1 and x is not equal to +1. Let's go ahead and box that in. That's our answer. I'm going to do another quick little example next to this one. Because I think it's good to have another example. Let's call this 1a, and then this next example will be like 1b. I'm just going to put a b right here. Let's pretend you were also asked to find the domain of the rational function g of x is equal to, and I'm going to make something up right now. Let's do something like, why don't we do, I think x minus 3 divided by, let's just go ahead and do x to the 4th plus 1. Now I want you to take a close look at this. Now, first of all, the denominator is what matters here, not the numerator. We're going to ignore the numerator. If I were to take this denominator, set it equal to 0, is there anything you could plug in for x to make this equal 0? I should restate that. Is there any real number that we could plug in? So this, we can't do this right here, not in our real number system, right? Unless we go into our complex number system. We're talking about complex numbers that are not real, but we're not doing that, right? Right now, we're working with functions in our real number system, and right now we can't take an even root of a negative number. So this would not be a real number here. So there are no numbers in our real number system that we could plug into this to make this denominator equal 0. Another way to think about this, if you have a variable raised to an even power, and you're going to add a positive number to that, right? If anything raised to an even power is going to be positive, okay? Or I should say non-negative at least. And if you add a positive number to that, well, there's no way you're ever going to make that equal 0. So is that clear that there's no way this could ever equal 0 in our real number system? So our domain for this is just basically going to be all the reals, all the real numbers. We could write it as the open interval from -infinity to infinity, or the set of all x such that x is an element of the set of real numbers. And that's it. Okay, so sometimes you come across problems like this where, yes, you've got a rational function. Yes, you have variables in the denominator, but even though you have variables in the denominator of a rational function, you're still going to have your domain be the set of all real numbers, because no matter what real number you choose, nothing will make that denominator equal 0. All right, let's go into finding vertical asymptotes of a rational function. Let's do an example here, a quick little example, just to make this a little bit more, it's easier to understand. F of x is equal to 1 over the quantity x plus 3, right? Quantity squared. Notice that the x plus 3 here, I've got 2 factors of it since it's being squared. I just have to basically set one factor equal to 0 to solve to find my restrictions on my domain. And basically it says here x equal to -3. So if I plug in -3, that will give me a 0. And what's going to happen at that x equal to -3 is I'm going to end up with what's called a vertical asymptote. And this was going to be represented with a dashed line. We're going to write the equation of this with an x equal to -3. Now I'm just going to go ahead and I'm going to go to switch to the graphing calculator here real fast to show you what the graph of this rational function looks like, right? So you guys buy into this idea of what we're talking about here, what's happening as this function is getting close to this vertical asymptote. So let's go ahead and switch over to our graphing calculator. I've already typed in the rational function. As you can see, I'm pretty fast. Yes, that's right. And I'm just going to show you the window settings so you can see what window settings I used. I really wanted to zoom in here on this rational function so it was very clear what was happening. Now let's go ahead and graph it. There's our rational function. So do you see what's happening here? Look at what's happening as we're getting close to x equal to -3. There is no dashed line here, right? Because the dashed line's not part of the graph, right? It's like there's an imaginary line there. But the graph of the function is never touching anywhere here at x equal to -3. And if I were to go to the table of values, look what happens. At x equal to -3, it says, why? Error. That's because there can be no y value at x equal to -3 because the function is undefined at that value. That's why we have a vertical asymptote there at that value. Okay, so now we know what the function looks like. I'm going to go ahead and draw a quick sketch of this graph right here. Doesn't have to be perfect. It's just so you have an example on your notes here. So it looks something like this. The closer and closer that x approaches x equal to -3, it looks like our y values are going up to infinity, right? You guys agree? It's like shooting up there, right? Getting very, very close to the vertical asymptote, but never quite touching it. Let's do another example over here. This time let's do h of x is equal to, I'm going to do x minus 2 quantity cubed. And this time, let's look for our restriction, where I'm going to take our factor here. We have 3 factors basically of x minus 2 in the denominator. I'm just going to set one of those factors equal to 0 and solve. I get x equal to +2. That basically means that we have a vertical asymptote at x equal to +2. Now I'm not going to go ahead and do this on the graphing calculator. You guys can do that on your own. I'm going to go ahead and just draw my vertical asymptote. I'm going to label it. And I'm also going to draw you a quick sketch here of what the graph looks like without going to the graphing calculator, because I've already taught you that you can use your graphing calculator to see the sketches of these rational functions, or to see the graphs of them. It's going to look something like this. On the left-hand side, notice how as we get closer and closer to the vertical asymptote, it's going to go down to -infinity. And on the right-hand side, as we get closer and closer to the vertical asymptote, it's going to go up towards +infinity. Okay, so notice the differences between these two rational functions that we did right here. Okay, they do look a little bit different. On the left-hand side, it said, if you look in the small print here where it says C, as x approaches C from the left-hand side, then r of x goes to infinity. And look at the graphs, right? You can see over here for the C one, they are going up to infinity for our y values. And on the D example, one's going to -infinity and one's going to +infinity. This has to do with the multiplicity of the factors. So that's what it has to do with. Notice how this multiplicity of this one, h of x, is odd. It's an odd power. That means it's an odd multiplicity. And then we have the one over here on the left where we had x plus 3 quantity squared, which is an even power. That means it's an even multiplicity, right? So as I was reading this C part where it said, as x approaches C from the left-hand side, then r of x is going to approach infinity. Whenever you raise any negative number to and whether you put in negative values in there, right? It doesn't matter. And not that the C going how can I say this? This part right here where it says as x approaches C from the left-hand side, this part, it does happen to give us negative values for this particular example, but even though we have a negative value in there that's going to get squared, it's still going to go to +infinity, okay? I'm going to write this out so you guys can see how this is said out loud. So this part where it says where the x and has the arrow to the c with that negative like superscript, it says as x approaches c from the left. Has nothing to do with, it doesn't have to be negative. In this case, they are negative values on this side, but they don't have to be negative. It just means that it's coming in from the left-hand side of the vertical asymptote. And then as we're, so this is coming in from the left, and then as we're approaching from the other side, we say that we're approaching from the right-hand side to C. So then that would be the second part here where it says as x approaches C from the right, okay? I need some more space here. Let me make up some more space so I can write this all out. Okay, so we did, now we're ready to do the second one. The second one says as x approaches C from the right. So even though it looks like, you know, that's talking about positive numbers, that's not positive numbers. That little plus sign and the superscript, like the exponent part on that C, it just means we're coming in from the right-hand side. And notice that as we're coming in from the right, in this particular example, we do happen to have negative values that are coming in from the right here. You know, we're coming in from positive infinity, but as the closer and closer we get to x equal to C, actually, we happen to be on the negative side here for this particular example that I did as we get very close to C. But that's not what matters. What matters is that we're coming in from the right-hand side to that vertical asymptote. That's what it means. We're coming in from the right. And as x approaches C from the right, then r of x is approaching infinity, right? Because once again, you're raising something to an even power. And if you raise something to an even power, it's going to go towards positive infinity, because whenever you raise something to an even power, it's always going to end up being positive. And then the same thing's happening over here on the right. I'm not going to write out the ones for the right. You guys can read that on your own. For the D, as x approaches C from the left, then r of x approaches negative infinity. That's because of the odd power. You can't have negative numbers for that one. And as x approaches C from the right, then r of x approaches positive infinity. So I'm not going to write out in the way I wrote out the words for the other one. But you can see here, I can just show you. This represents as x approaches C from the left, and you can see we're going down towards negative infinity here. And then we're raising the whatever we have here, the x minus 2, it's going to end up being a negative value. And when you raise a negative value to the third power, it's going to end up being negative, so it's going to go down towards negative infinity. And when we're coming in from the right here, you see here we're at 3, 4, we're at numbers that are they're bigger than, right, -2 here. So they're going to end up being positive. And when you raise a positive number to an odd power, it's going to be positive. It's going to go up to positive infinity. Now I'm trying to make this connection here with these examples that I have written down here. So these first two say odd multiplicity. So for A and B down here, you're going to refer to this example that I'm highlighting in blue. This is an example of odd multiplicity. So this is odd multiplicity. That first example that I have right there for A, that's going to represent an example that is with a positive version, like our h of x is a positive. And then the second one, I'm going to make up a new example. I'm going to put a -1 on top of this one. It's like we're multiplying the function by a negative. So when you multiply a function by a negative, as we learned from our transformations, it gets reflected across the x-axis. So that's why it looks like it's been reflected. Whereas the first one, our h of x, that I'm just going to copy down our last example that we did right here, this one, right? It looks exactly the same as the last one that we just did. Okay, so whenever you multiply a function by a negative, it gets reflected across the x-axis, right? And these two examples here, those were odd multiplicity. The next two that I'm doing here, this is going to be examples of even multiplicity. And that you're going to refer to this first example that we did here. I'm highlighting it in green. I'm going to draw an arrow pointing towards this example. So this would be this first example of a positive version of our function with a even multiplicity. So that would be for C. And for D, imagine if I multiplied the function by a negative, it would flip it across the x-axis. So that's why it looks like a reflection across the x-axis. So those would be examples of even multiplicity. So I'm just going to go ahead and do an example here, a quick example, just write it out so you guys have it written on your notes. So for example, let's say I took that same function that I was working with. Well, let me change the value of the denominator because looking at this example here, this one has a vertical asymptote at x equal to 2. So I'm going to do x minus 2 here for my factor in the denominator so that it matches up with this graph nicely. So this one says x equals 2 is the equation of the vertical asymptote. So I'm going to write x minus 2, quantity squared. So you can see that this one, because there's a negative in the 1 here, since we multiplied our function by a negative value, it just basically reflects our function across the x-axis. So instead of going up towards positive infinity, as the closer and closer we get to the vertical asymptote, we're going down towards negative infinity. All right, let's talk about how to find a vertical asymptote. Theorem. So locating vertical asymptote. So the graph of a rational function r of x equal to p of x divided by q of x in lowest terms, and this is important in order to find vertical asymptotes. This time the rational function does need to be in the lowest terms for you to identify vertical asymptotes, okay? Whereas this might not have been important when we were finding domain and I said it didn't matter, you didn't worry about the numerator. This time you do have to worry about making sure it's in lowest terms. So the graph of a rational function r of x equal to p of x divided by q of x in lowest terms has a vertical asymptote x equal to r if r is a real zero of the denominator. Q. Okay, so I think that pretty much says everything there. Now let's write a little bit more. That is, if x minus r is a factor of the denominator. Q of the rational function r of x, or r, in lowest terms. So once again, that's key. The lowest terms part. You need to make sure it's in lowest terms. Oh. So it says here, that is if x minus r is a factor of the denominator q of the rational function r in lowest terms, the graph of r has a vertical asymptote x equal to r. All right, so I think now we're ready to find vertical asymptotes. Let's go to number 2. Find the vertical asymptotes, if any, of each rational function. Well, the first thing I need to do in order to find a vertical asymptote, right, is I'm going to need to take my denominator. Well, first I need to make sure it's in lowest terms. Number 1. I can tell that 2a is in lowest terms because if you look at the numerator and you look at the denominator of that rational function, I can tell that there are no common factors. The only factors of the numerator are going to be factors of x, right? It's got 3 factors of x in the numerator. And the denominator, x to the 4th minus 1, I can tell that those, if I were to factor out that polynomial, there are no factors of x in that, because the factors of x to the 4th minus 1, that's the difference of 2 perfect squares. It's not going to factor into any single factors of x. So what I need to do is I just need to worry about focusing on the denominator and setting it equal to 0 and solving it. I could do that 2 different ways. In this case, I could find it by setting it equal to 0 this way and solving for x, which I've already done in that very first problem we did. Another option would be to factor this out. Since it's the difference of 2 perfect squares, it will factor into x squared plus 1 times x squared minus 1 equals 0. And the x squared minus 1 is the difference of 2 squares again, so I could factor that out some more. So it would turn into these 3 factors of x squared plus 1 times x plus 1 times x minus 1. And then if I set these factors equal to 0, the x plus 1 and the x minus 1, I could solve those. Notice I am not setting the x squared plus 1 equal to 0. Why is that? Because there are no real solutions for that if I were to set that equal to 0. So if I have x squared plus 1, and I try to set that equal to 0 and I try to solve it, it's just going to give me no real solutions. Because we talked about this. If you square something, if you square a number, there's no way it can be negative, right? And then if you add a positive number to a non-negative number, there's no way you're ever going to make it equal 0. So I'm not even going to worry about that factor. So my only vertical asymptotes are going to be here at x equal to a negative 1 and x equal to positive 1. And that's it. Let's go ahead and box that in. That's our answer. That's our final answer for that problem. All right, let's go to B. All right, this one, I definitely need to factor these out. These have leading coefficients that are not 1s, so whenever we have any trinomial of this form that can be factored and its leading coefficient is not a 1, I like to use the factoring by grouping method, so that's what I'm going to use. You guys can use trial and error to factor this out, and that's perfectly fine. But I'm going to use factoring by grouping. So my factors come out to x minus 4 and 2x plus 3. So hopefully you guys got those same factors for that trinomial. Now I'm going to factor the 3x squared minus 11x minus 4. And once again, I'm going to use factoring by grouping because my leading coefficient is not a 1. So I'm going to turn this into a polynomial of 4 terms. Factor by grouping. And now I can take out a factor of x minus 4, and I'm left with 3x plus 1. So my factors are x minus 4 times 3x plus 1 for that denominator. So I'm going to rewrite g of x in factored form. So for the numerator, I've got x minus 4 times the quantity 2x plus 3 over the denominator, which is going to be x minus 4 times the quantity 3x plus 1. Are there any common factors? Yes, there are. I can cancel out here a common factor of that x minus 4. So remember that we said when looking for vertical asymptotes, our rational function must be in lowest terms. This is very important. I know that there is no way going to be a vertical asymptote at x equal to 4, okay? Now, if I had said find the domain, then that would have been a totally different problem. I want you to know that for the domain, 4 is still not allowed to be in the domain. So if I said find the domain, your answer would have been the set of all x such that x cannot equal 4. And x cannot equal, well, I'd need to set that denominator equal to 0, right? That other factor, and solve it. Why don't I go ahead and just do that, because I'm going to have to do that to find the vertical asymptote anyways. So if I set 3x plus 1 equal to 0 and I solve, I'm going to end up with x equal to negative 1/3. So this is another restricted value in the domain. Okay, but notice the differences here. You guys need to make sure you make a big deal about this on your notes. For the domain, we still cannot have 4 in the domain. But in terms of vertical asymptotes, only x equal to negative 1/3 will represent a vertical asymptote. Okay, we need to make sure that this is very clear for everyone. And sometimes there's a lot of confusion between this. Why? And they're like, why? Why is that? Why is it that the x equal to 4 is not a vertical asymptote? Something else is happening at x equal to 4, okay? I'm going to go ahead and just write a little note about what's happening at x equal to 4. We're going to be talking about this later on in future sections. But basically what's happening at x equal to 4 is we have something else occurring there. We have something that's called a hole. So at x equal to 4, we basically have a hole. It's like an open circle. That's what it is. And to find that exact, the coordinates of that point where we have that open circle, you would basically plug in x equal to 4 into the reduced version of the rational function, right? You can't put it into the original function because it's undefined at x equal to 4. But if you put it into the reduced version, it will give you the coordinates, right? The x, we already know the x coordinate. It would provide you with the y coordinate of that hole, that open circle of the function. All right, let's go ahead. Let's find horizontal and oblique asymptotes of a rational function. So these first two examples that I have drawn here already, these show examples of horizontal asymptotes. All right. So notice it says here, in behavior as x approaches infinity, then r of x will approach L. And as x approaches negative infinity, then r of x will approach L. Basically, whether you go to negative infinity or positive infinity, y is going to approach a specific value, a constant value, and you're going to end up with a horizontal asymptote. An oblique asymptote. Another word for an oblique asymptote is a slant asymptote. Okay? So a slant asymptote or an oblique asymptote is going to be an asymptote that is, how can I explain this? It looks like a linear, kind of like a linear function. It's a kind of like the word slant. What's it make you think of? Kind of like a slanted line, maybe? So it's basically just going to be a line that's kind of like it's got some, tilt, some slope to it, some tilt, or some, it's not perfectly horizontal, or it's not perfectly vertical, right? So it'd be one of those other type of lines, a line that is not vertical and not horizontal. It's going to look like one of those lines. I'm just going to draw a line here as an example, so you have an example in your notes to refer to. So this dashed line that I'm drawing here at an angle, I'm trying to draw this like at a 45-degree angle here. This is supposed to represent y equal to x. So this would be an example of an oblique asymptote or a slant asymptote. And I'm just going to draw an example of a rational function that would use this here to help, like we would use it to help guide us graph this rational function. So this would be our oblique asymptote, or another word for oblique, slant asymptote. And y is basically going to approach this line, like y equal to x, as it goes to infinity. As x goes to infinity, y will approach basically x. Okay, let's talk about the directions for finding these horizontal or oblique asymptotes. So I'm going to write out the instructions here, or the steps you would take in order to find these. Yeah, let's go ahead and first write down like the general form of a rational function. So let's consider the rational function r of x is equal to p of x divided by q of x. And what I'm going to write down here, it's just a general form that we use for writing down a polynomial function. So a sub n of x raised to the n plus a sub n minus 1 of x raised to the n minus 1 plus an ellipses, so on, plus a sub 1 x plus a sub 0. That a sub 0 represents our constant usually at the end there. So it's the general form of writing a polynomial. And I'm going to write another one here, and this time in terms of b and m here. B sub m times x raised to the m power plus b sub m minus 1 times x raised to the m minus 1 power plus so on, plus b sub 1x plus b sub 0. Okay, so these just basically represent like the different terms you can have here. This first set of terms represents our leading terms of each one of these polynomial functions. They are the ones that represent the degree of the polynomial. So notice I'm highlighting the degree. For the numerator, the degree is n. For the denominator, the degree is m. And we use these leading terms, right? When our polynomial is written in descending order like this, we use these leading terms to determine what type of asymptotes our rational function is going to have. So there's basically 4 different cases that can happen here. So what I'm going to attempt to do is I'm going to attempt to try to separate this into 4 segments or 4 cells or boxes. And I'm going to try my best to just try to make them look like they're evenly spaced, because those of you that know me, you know I'm a little bit of a perfectionist, and it bothers me when things don't look like it's like perfect. I try to make it look nice. I can't do everything perfectly, but I know this does not look straight. We're just going to use our imagination, and we're going to pretend that all of these line segments are drawn perfectly perpendicular here, and that they are all of equal length, and that these little, that I tried to draw these square or rectangular sections so they were all equal. And yeah, we're just going to do that, and we're going to move on with our lives, and we're not going to worry about it if it's not perfect. All right, so there we go. That's as good as it's going to get. Let's go ahead and write in what we're going to put in the first box here. Our first case scenario. So for our first case that we're going to write here in our box, once again, I said we're looking at the leading terms. We're going to look at what happens if n is less than m. So what does that mean? N is less than, strictly less than m? It basically means that the degree of the numerator is less than the degree of the denominator. So if the degree of the numerator is less than the degree of the denominator, this is what's going to happen. You are going to basically have a horizontal asymptote at y equal to 0. Y equal to 0 is a horizontal asymptote to our rational function. Okay, next case, n equals m. So what does this mean? Basically means that the degree of our numerator is going to be exactly equal to the degree of our denominator. So if the degree of our numerator equals the degree of our denominator, then that means we're going to have a horizontal asymptote at y equal to a to the n over b, I'm sorry, a sub n, I meant a sub n. Y is equal to a sub n over b sub m. The coefficients, you're basically taking the coefficient of that leading term, and that's going to be your new numerator for this horizontal asymptote. And you're taking the coefficient of the leading term for the denominator, and that's going to be the denominator of this horizontal asymptote. Imagine that your x raised to the n and your x raised to the m, since they're equal in degree, right? You can cancel them out because they're equal to each other, and you're basically going to just be left with these coefficients, okay? That's what's basically happening here. All right, so that would be our horizontal asymptote when n equals m. Now, what about if n is equal to m plus 1? If the degree of the numerator, or the degree of the polynomial in the numerator, is exactly 1 more than the degree of the polynomial in the denominator, then what happens? Well, then this would be an example of where we would have a slant or an oblique asymptote. Y is going to be equal to like a linear function here. Y is equal to ax plus b is going to be our oblique asymptote or our slant asymptote. Now I know what you're thinking. You're thinking, how do I come up with this linear equation for this slant asymptote or this oblique asymptote? Where am I supposed to come up with this, right? Well, let me tell you how you're supposed to come up with that. That's going to be found by doing a little bit of what I like to call polynomial division. You guys should already know how to divide polynomials. You can divide polynomials by using a little something called long division. Yay. I know you guys, everybody's heart just went like, oh, yay. And, or in some cases, you might be able to use synthetic division if your divisor is of a specific form. So synthetic division doesn't always work. Unfortunately, we're just going to write down the word sometimes. It sometimes works. But if you want to make sure it always works, then always just use long division. That will always work. Okay? All right, what about when n is greater than or equal to m plus 2? So when n is greater than or equal to m plus 2, there will be no horizontal or oblique asymptote. And that's basically it. These are your 4 cases. Isn't that cool? That's all you have to worry about. Not too much. Not too bad, right? Like I like to say, not too bad. So just go ahead and memorize these 4 cases, which is not too bad. Draw a poster of this, put it up on your wall, in your room, and it won't be too bad. So, the end behavior for something that looks like this, where you have n is greater than or equal to m plus 2 for those degrees. The end behavior of the graph resembled y is equal to a sub n over b sub m times x raised to the n minus m. So that's what the end behavior is going to look like for a rational function of that type. Oh, and I also want to mention one more thing before we get past this part right here. A special note right here. Note. Let's put a little star. A rational function never has both a horizontal asymptote and an oblique asymptote. It's either one or the other. It's either, or you might not have, either one, right? Because it's possible that it doesn't have to have either one of those. But you can't have both of them in one of the rational functions, right? So that's it. I think I stated everything we need to know about horizontal and oblique asymptotes. Yeah, I think that's pretty good. All right, I think now we're ready to go on to the next problem. The next problem says find the vertical, horizontal, and oblique asymptotes, if any, of each rational function. The rational function we're going to be working with here for number 3 says f of x is equal to x squared plus 6x plus 5 all over 2x squared plus 7x plus 5. So guess what I'm going to do first? I'm probably going to try doing a little bit of factoring first, because I already know that in order to find vertical asymptotes, I need to set my denominator equal to 0, but my rational function must be in lowest terms. So I just want to make sure that this is reduced and that there are in fact no common factors between our numerator and our denominator. Okay, so that's what we're trying to do first. I do not have a leading coefficient here for my denominator, so I am going to factor by grouping, because I like to do factoring by grouping when I do not have a leading term with a leading coefficient of 1 for my trinomials. I end up with the factors of x plus 1 and 2x plus 5. So hopefully that's what you guys got. Once again, if you guys want to use trial and error, that's fine. For this one, because I do have a leading coefficient of 1 in the numerator, I'm just going to go straight to the factors. I'm not going to do factoring by grouping. I'm just going to write the factors just from here, from using my magic x. So I'm just going to write x plus 2 and x plus 3. Looking at these two sets of factors, there are no common factors. So there is nothing that I can reduce here. I am going to have to to get my vertical asymptotes, I'm going to have to use both of those factors in the denominator and set them both equal to 0 to find my vertical asymptotes. I'm just going to rewrite my function right over here in factored form. And there we go. All right, so now that I did that, I'm ready to set each one of my factors in my denominator equal to 0. So we're going to set x plus 1 equal to 0 and solve for x. So I'm going to get x is equal to a -1. That's one of my vertical asymptotes. And I'm going to set 2x plus 5 equal to 0 and solve for x. That's going to give me 2x is equal to -5. Divide both sides by 2. So I'm going to get x is equal to -5/2. All right. So those would represent my two equations for my vertical asymptote. So in this case, I have two vertical asymptotes. Let's go ahead and write that down before I forget. All right, now we're ready to find our horizontal and, or I should say, or oblique, or maybe neither. Let's see, what am I looking for here? I'm looking at the leading terms. I've got x squared over 2x squared. What can you tell me about these degrees? Which one of these categories does this fall into? I've got x squared over x squared. This looks like that second case, where n is equal to m. 2 is equal to 2. The degrees are equal to each other. So imagine I were to cancel these out. What would be left? I would just have like 1 over 2, right? So basically my horizontal asymptote is going to be y equal to 1 over 2, or y equal to 1/2. And that's it. It's as easy as that. Okay, but let me go ahead and write down the steps here for anyone that needs to see this written down. So this is going to be our horizontal asymptote. It's going to be so we had x squared over 2. Oops, let me erase that. We had y basically equal to, we have x squared over like our 2x squared. And what I basically just did here is I basically, since the degrees are the same, I just kind of ignore the x's and I just look at the coefficients of those leading terms. And so that's going to end up giving me like that 1/2. So we're basically going to write here, our horizontal asymptote is y equal to 1/2. And yeah, that's it. We covered everything there, right? Everyone agree? And a rational function never has both a horizontal and oblique, so I'm done. I'm not going to keep on trying to find an oblique asymptote because it can't have one. You can either have horizontal asymptote or an oblique, or maybe you have neither, right? But you can't have both of them. Let's go ahead and write down our final answer here. For vertical asymptotes, we had x equal to -1 and x equal to -5/2. For horizontal asymptote, we had y equal to 1/2. Let's box that in, and that's our final answer. All right, let's go on to the next problem. Yay! These are fun. Number 4, p of x is equal to 4x squared over x cubed minus 1. All right, so let's look at this. I can tell by looking at this right away that there are no common factors between my numerator and my denominator, so I don't have to worry about trying to write this in lowest terms. So there's no point to that. I do have to worry about that denominator, about factoring it out, because notice what we have here. We've got x cubed minus 1. This is the difference of 2 perfect cubes. And we have a special formula for factoring these type of polynomials out. All right? I'm going to write this out. This is the difference of 2 cubes. Yes. So that formula, hopefully you guys remember it from factoring. We've discussed all our factoring techniques earlier on in the semester. A cubed minus b cubed is equal to the quantity a minus b times the quantity a squared plus ab plus b squared. Hopefully this looks familiar. I need to make sure that I factor this out correctly and that there aren't, any possible zeros, real zeros that I miss. So if I factor this out, I'm going to get x cubed minus 1 is equal to x minus 1 times the quantity x squared plus x plus 1. Now, x minus 1, that's an easy one to set equal to 0. I'm just going to get x equal to 1. The problem is with this second trinomial. I think I told you guys you can't factor out these trinomials that come out of the sum or difference of 2 cubes. Right? Do you remember I mentioned that? That means we have to use either completing the square or the quadratic formula. Before I start using something like the quadratic formula, I'm going to just look for the discriminant to see, should I even bother doing this? Does this have any real solutions? So if I find the discriminant, it will tell me that. The discriminant ends up giving me -3. So imagine this is the part that's underneath the square root. If you have a -3 underneath the square root, what can you tell me about that? That's right, it's going to be an imaginary number, right? So what this is basically saying, if I were to set this equal to 0, this trinomial, and try to solve it, I would end up with no real solutions. That's what it's telling me. So I'm not going to even bother wasting my time trying to use the quadratic formula for this, because this has no real solutions. Good. So then what basically this is all telling me, I've only got one vertical asymptote. My only vertical asymptote here is going to be at x equal to 1. And that's it. All right, let's go ahead and worry about, does this have any horizontal or oblique asymptotes? I'm going to focus on the leading terms. I got 4x squared over x cubed. So do you recall what this means when you have x squared over x cubed? When the degree in the denominator is larger than the degree in the numerator, or n is less than m. Do you remember what that means? Maybe we need to go back and refer to our little chart that we just did. What happens when we have something like this, when n is less than m? Imagine I were to put very large numbers in place of x. What would happen? This would basically, if the larger that x gets, as x approaches infinity, imagine x is approaching infinity, what's going to happen to the overall number here? This is basically going to go to 0, right? That's what's going to happen. Also, imagine I were to cancel out like the 2 factors of x on top with the 2 factors of the x on the bottom. You'd still have a factor of x on the bottom. So if I were to put in a very large number and divide 4 by a very large number, it would go to 0. Okay? So basically what that means, whenever n is less than m, it's basically saying this. Y equal to 0 is going to be a horizontal asymptote. That's what it's basically saying. Okay? So let's go ahead and write that down. So 2 is less than 3. N is less than m. So our horizontal asymptote is going to be y equal to 0. Y equal to 0 is a horizontal asymptote. All right, good job. Yes. Vertical asymptote at x equal to 1. Horizontal asymptote at y equal to 0. Bam, we're done. Let's box our final answer and let's move on. Our next rational function says g of x is equal to x cubed plus 1 over x squared minus 5x minus 14. Yay! Let's go ahead and why don't we focus on finding the factors of the denominator first. I already can tell by looking at the numerator it's the sum of 2 cubes. But I don't want to have to worry about factoring it out if I already see that there's no common factors in the denominator with it. So let's factor the denominator first. And then we could factor out the numerator. If we happen to end up with like an x plus 1 in the denominator. So the denominator, I need two numbers that multiply to give negative 14 and add up to give negative 5. So that's going to give me x minus 7 and x plus 2. Yes, that works. Neither one of these factors is an x plus 1. So I'm not even going to bother to factor out that numerator because the numerator, like I said, okay, I will factor it out so you guys can see. The factors of the numerator are going to be x plus 1 times x squared minus x plus 1. There are no common factors. Therefore, I can't reduce this. I'm going to have to set each one of those factors in the denominator equal to 0 and solve in order to find my vertical asymptotes. There we go. We get x equal to 7 and we get x equal to a negative 2. Yes. So our vertical asymptotes are going to be at x equal to 7 and x equal to negative 2. All right, let's look at the leading terms of each one of these polynomials. I've got x cubed over x squared. That means the degree in the numerator is greater than the one in the denominator, but not just that, it's n is equal to m plus 1. The one in the numerator is greater than the denominator by 1, by a unit of 1. That means we have an oblique asymptote. And the only way we can find an oblique asymptote is by doing, yes, you guessed it, polynomial division. I can't use synthetic division for this one, unfortunately. Right? Because I don't have my polynomial in the denominator is not of the form that I need it to be, right? It needs to be something like an x, just like an x minus r type of form. That means we have to do long division. Yeah, I know. I know what everyone's feeling right now. Joy. Joy in their hearts. You're feeling it. I know. Accept it. Embrace it. Be one with it. Yes. So in order to find this oblique asymptote, the only way we're going to find it is if we do some long division here to find this oblique asymptote. So nice polynomial division, some nice long division. All right, hopefully you guys already know how to divide polynomials using long division. I'm just going to go ahead and set this up. So we're going to put our divisor out first, x squared minus 5x minus 14. And we're going to divide into our numerator, which is the x cubed plus 1. We're going to focus, make sure they're both in descending order. Focus on the leading terms. What do I need to multiply x squared by to turn it into x cubed? Well, I need to multiply by x. So imagine I'm going to distribute this x to all three of these terms in the divisor. I'm going to get x cubed minus 5x squared minus 14x. Notice that I'm writing these terms out here to the side because they're not common terms with that 1, right? So I'm just trying to make sure like things line up in a nice way. The x cubes are going to cancel out because I'm going to have to subtract this. And I'm going to end up with, I'm going to write this in descending order, 5x squared plus 14x plus 1. Now we do it again. What do I need to multiply the x squared by? By 5. So now we're going to distribute the 5 to each one of those terms in that trinomial. So if I distribute the 5, what am I going to get? I'm going to get 5 times x squared is 5x squared. 5 times negative 5x is negative 25x. 5 times negative 14, I believe that's negative 70. Yes, I think so. Now we're going to subtract this polynomial. So I'm going to change the signs. Minus, plus, plus. The 5x squareds cancel out. And then if I add those together, I'm going to end up with a 39x plus 71, I believe. Now this is what I would call the remainder here. So the remainder, what we usually do here is we usually just add it here at the end. We write 39x plus 71 over the divisor, the x squared minus 5x minus 14. Notice I'm doing it in a different color. I'm using green because this part isn't really the important part. It's not the part that we really want. We only want the part that's in blue in front. That's going to represent the equation of our oblique asymptote. So I'm going to put a little red cloud and highlight the part that I want in yellow. Okay? We're going to ignore the remainder part because if you look at the leading terms in the remainder part, if you were to imagine what happens as x gets very large, you can imagine what's going to happen there. That thing's going to go to 0, right? That thing's going to basically disappear. It's going to become insignificant. And the only part that really matters is that y equals to x plus 5 part. And that's our oblique asymptote equation. That's the part that matters. That's the part that we want. So that's it. We're done. We finished. Yay! Yay for you guys. I'm so proud of you guys. You made it to the end of this video. Excellent. Good job. All right. So until next time, have fun doing your math. Okay. I'll see you guys. Bye-bye.